Today we'll start off with topic number 3A. Topic number 3 is divided into 3A and 3B. Today we'll cover all of 3A and tomorrow we'll cover all of 3B. So waves and the particle nature of light. Okay. Let's talk about some basics of the waves that you've known from IGCSE as well. Okay. And over here, what we'll need some skills is regarding the unit of frequency, which is hertz. What is the speed of light? You should know it is 3 into 10 to the power 8. Then
23.
the wave equation as well. V is equal to F lambda. And then comparing the two equations and finding distances as well. So in this chapter, what will I study later? If we talk about 3B, we'll talk about how waves combine when they meet. Topic 3C will tell us the properties. Topic 3D will tell us the wave particle duality and much. So wave is means for transferring energy via oscillations. Because if someone asks you, does wave transfer energy? What is wave? Wave is a energy carrier. It carries energy. Just imagine it can carry anything. For example, if you throw a piece of ball, okay, if you just throw a ball on water, it's gonna float. It's gonna change distance, which means there is an energy that has transferred the ball from one point to the other. A wave is means for transferring energy via oscillations. If this is a wave, if a ball is over here, it's gonna travel up to this point after a short while, which is the proof that energy transfers with oscillations. Whilst the energy moves from one place to another, the waves cause no net movement of any matter. A mechanical wave is the one in which there needs to be some sort of material medium, a substance that oscillates to allow the transfer of energy. For example, a sound wave of human voice transfers energy from one person, vocal cord, sound waves hoti hai. Now, how does sound carries? Okay, sound travels by vibrations. It's a longitudinal vibrations, repeated vibrations hoti hain in air molecules. If there is no air around us, I cannot hear you what you're saying. I can hear you what you're saying because there is air in the medium. We do not live in a vacuum. There are air particles that are going to carry your voice to me. Electromagnetic waves can transfer energy through repeated oscillations of electric and magnetic field, but these fields do not need matter to support them. Indeed, the interaction between electromagnetic waves and matter generally slows their transfer of energy. For example, light travels more slowly in water than it does in vacuum. So if you look at a wave,
Right.
you have displacement on the y-axis and distance on the x-axis. So this is one wave, starting from here to here, or starting from here to here, or you can say starting from this point to this point. So this is one wave. We call it the
Yeah.
wavelength when we are given distance on the x-axis. Then this is the amplitude, the displacement.
Mm-hmm.
Amplitude is the maximum displacement of a wave from its mean position. Then the highest point is known as crest and the lowest point is known as trough. Wave motion
Right.
can be plotted on graphs. A plot of the displacement against distance traveled for a wave, as in figure A, shows the physical scale of the oscillations and the movement of the energy. Alternatively, a plot of the displacement versus time in figure B shows how the vibrations occur over time as well. You can see, okay, this is if there is time on the x-axis, then the time period would be represented the same as it was one wave. Okay. So you always have to see
Right.
what is there on the x-axis. X-axis पे अगर time है, तो it's gonna tell you the time period. अगर x-axis के ऊपर distance दिया हुआ है, then वो आपका wave
That
की
will be
length है.
wavelengths.
Good job. There are a number of important properties of wave that scientists measure for various purposes. In most cases, you can determine these from the graphs shown in figure A and B. Displacement, for example, is the position of a particular point on a wave at particular instant in time measured as mean और वो आप x से measure कर लेते हो simple. जैसे amplitude is also measured, it is called x. Wavelength is not x. It is a distance, but it's not x. We use the sign lambda for this length of a wave. Amplitude is the magnitude of the maximum displacement reached by an oscillation of the wave from the mean position. If this is the mean position, the highest displacement reached is the amplitude. Frequency, on the other hand, is the number of complete wave cycles per second, and this may sometimes be measured as the number of complete waves passing a point per second. Wavelength is the distance between a point on a wave and the same point on the next cycle of the wave. Frequency क्या है? 1 second में कितनी waves pass कर रही हैं? 5 waves per second means 5 is the frequency. 10 waves per
Mm-hmm.
second means 10 hertz is the frequency.
10.
And period would be the time taken for one complete oscillation at one point on the wave. And this will also be the time taken for the wave to travel one wavelength. Phase, on the other hand, is the stage of a given point on a wave, which is through a complete cycle. Phase is measured in angles as a complete wave cycle and is considered to be traveling at the same around complete circle. अब complete circle का मतलब है 360 degrees, or we can also call it 2 pi radians. And you can पूरा एक circumference होता है जिसको हम 2 pi r से भी कह सकते हैं. Wave speed, the last but not the least property, is the rate of movement of the wave. Distance by time. ठीक है, ये आपको वेव स्पीड है, लेकिन हम इसको कैसे निकालेंगे? V is equal to F into
If
lambda. You can also find the speed of a wave from distance divided by time, as with the speed of anything. However, as each wave has a certain wavelength and the frequency tells us how many of these wavelengths pass per second, you can also find the speed by multiplying the frequency and wavelength together. Because frequency कैसे आती है? Frequency is 1 over t.
yep.
Good. Pulse echo measurements. Do you know how do bats communicate? Chamkader? Bats?
Bats?
Yeah. They
Oh,
are
bats are like the animal, yes. By I think squeaking, almost like
exactly,
echoing
exactly. That's squeaking. What is that squeaking? You're correct.
a frequency.
Frequency. That squeak has a frequency, but how? Because they're blind. Do you know bats
Yeah.
are blind? They don't have eye. Okay? They can't see. That squeaking
Mhm.
helps them to move. Take a guess. How is that possible?
I guess if when I guess when sound bounces away from wall, it knows that there's a wall
Exactly.
there.
Exactly. And what do they do then when it echoes back? They move. They
They
change the
move away
direction
from it.
because they don't want themselves to hit on the wall. Got it?
Yeah.
Known as pulse echo. The natural habitat for some bats is woodland and they fly through trees at 10 to 15 kilometers per hour. Now, this is not a very fast speed. It's nothing. It's very slow. In order to catch the insects, the bats need to be able to sense their location precisely. And their well-known echolocation system uses a very high frequency ultrasound and pulses, which is about 50 to 100 kilohertz. At greater distances, the echo is too quiet. So when they hear a very high echo, this means that a wall or a barrier or something is coming. But when the echo is too quiet, what will they do? They just keep going. But how
Hmm.
does it work? The bat will make a chirp sound, not a squeak. Squeak is like it's kind of like chirp through its nose, and the
Hmm.
sound pulse will typically last 3 milliseconds. When the sound hits nearby objects, it will be reflected back to the bat's sensitive ears, and its brain can accurately measure the time making the sound and hearing the echo. The bat's brain has
To know
also
how far away it is.
exactly बिल्कुल उसके ears बहुत sensitive हैं. God has given
Hmm.
them no eyes, but God has given them very, very sensitive ears, even more sensitive than ours, that they can hear the tiniest echo as well. So,
Yeah.
you know,
They can hear at a lower frequency.
exactly, exactly. That is why they can even see that how far distance there is a wall. We can't hear that echo. Distance equal to speed into time. Experiments with dolphins have also shown that they use similarly echolocation system. Even the sonar system. If you've seen the movies, ships, how do they track ships? Sonar. That is also sonar. They throw away sound pulses everywhere in the ocean, and then the sound pulse just bounces back and tells them the location on the radar. That is also known
Right.
as sonar. Or the boats also use sonar to check the depth of the ocean, how deep the water is. ये भी sonar
Yeah.
system होता है उनका, because they have to anchor their ships as well. They probably
Hmm.
also true for the bats to ensure that they eat an insect and do not eat an insect sizely, but dolphins can respond to experimental scientists better. We have developed similar pulse echo ranging and imaging systems in very wide range of technological applications, from sonar on ships and submarines, air traffic control. Oh, I forgot this as air traffic control कैसे करता है? How are aeroplanes seen? Because they don't have any Wi-Fi connection. What do?
Yeah.
Sonar. वो भी तो
Uh,
सोनार है. हमारे पास इतने बड़े
yeah.
towers होते हैं. They throw away the pulses as well. Airports पे they can see how far the plane is. Then at a certain distance, yes, then they can restore their connection as well. This is
Yeah.
particularly useful in situations where other methods might be difficult or dangerous. For example, Venus has a very hot high pressure. अब कुछ atmospheres में ये चीज नहीं चल सकती, because what did I tell
Yep.
you in the start? Waves हैं. Waves
Yeah.
depend on medium as well. If you're thinking that the waves travel the same speed in water than in air, it's not. It's a different
Yeah. It
speed.
will slow down.
एग्जैक्टली exactly. अब वीनस की एग्जांपल दे रहे हैं, मून तक भी ठीक है। वीनस का एटमॉस्फेयर इज वेरी हॉट, डेंस क्लाउड्स हैं, दे कैन ब्लॉक
Mhm.
वहां पे कम्युनिकेशन सिस्टम वीनस पे या मार्स पे।
Even the air can block it.
क्योंकि एयर ब्लॉक कर देगी, आपके एयर पार्टिकल्स डिपेंड करते हैं, एयर पार्टिकल्स आर द वंस दैट हैव टू वाइब्रेट। अब हैवी एयर होगी तो ब्लॉक हो जाता सब कुछ। Air traffic control system sends out a pulse of radio waves that are reflected by a jumbo jet. The reflection is picked up by the radio dish 0.07 seconds after the emission of the pulse. How far away is the plane? So पहले आप निकाल लो स्पीड हमने निकालनी है, ठीक है? नहीं, we have to calculate distance. How far? Distance is equal to speed into time. Now the speed, अब उन्होंने यहाँ पे how do you know what's the speed?
Uh, So 3 times.
Radio waves. Radio waves is a electromagnetic wave, remember?
Mm-hmm.
And all electromagnetic waves have speed of light. कौन कौन सी होती है
Yeah.
electromagnetic waves? Can you tell me the spectrum?
Radio waves.
Next.
Not sound waves. Light. No, no.
Good. ठीक है.
Uh,
Microwave, gamma rays, X-ray, infrared, ultraviolet.
Alpha rays.
या एग्जैक्टली, वो भी स्पेक्ट्रम हमने आगे पढ़ना है इन 3B, टॉपिक नंबर 3B के अंदर। दे ऑल ट्रेवल एट, सो एग्जामिनर इज नॉट गोना टेल यू द स्पीड. You should know that this is an electromagnetic wave and the time is given to you. Multiply the speed with time and you'll get the distance. Got it?
Yeah.
Good. Now, the thing is that the distance you have calculated, is this the distance? No. Distance आपका ये डबल हुआ है. Actual distance आपने इसको divide by 2 करना है. Why is that? Can you tell me?
Divided by 2.
Why have we divided the distance by 2 at the end?
Because
जो हमने distance निकाला वो क्या था? This is the air control
yes,
tower and this is the
yeah,
aeroplane. You sent a pulse, the pulse came back.
yeah.
If I
So
ask
it will need
how
double
far
the
was the
time, so we
plane?
divided by 2. So
Exactly,
you know the distance.
exactly. अब ये जो
So
पूरा
it
पल्स
traveled doubled. So
था 2100. This is
yeah,
how far the plane is. Plane is only half of the distance far है,
yeah,
क्योंकि बाउंस बैक होके वापस आ रही है. तो स्टूडेंट्स यूजुअली फॉरगेट दिस स्टेप and they always finish their equation over here. Whenever it's an echo question, remember echo double distance होता है. आपने half करना distance को, then you'll know that how far the plane actually is. Got it?
yeah,
What are the amplitudes of the three waves shown? 0.2, 80, 5.5. Got it?
yeah.
So these are all the formulas. I won't read them out. We'll move on to the types of waves. Okay. There are two types of waves, transverse and longitudinal. Do you remember what's the difference between these two? Hmm. What is the difference between transverse and longitudinal waves?
Transverse waves, they are shorter, I think, but higher frequency.
Mhm. Kind of, yes.
And I wasn't and wavelengths, they have lower frequency but longer wavelength.
Okay. ठीक है जी.
Hi and welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to describe wave motion in terms of amplitude, wavelength, frequency, and period. Now, some of these ideas can seem a little bit tricky at first, but I'll show you exactly what they mean, and you'll see they're quite straightforward. Okay, I'm showing you here a transverse wave, and we looked at these in a previous video. Now, all waves have got certain key features, which you've got to be able to label. We're going to start by looking at the amplitude. I'm showing you the definition of amplitude here. The amplitude of a wave is the maximum displacement of a point on a wave away from its undisturbed position. So what does that actually mean? If we look at the wave, we can see a point in the center where the wave is not moving, and I'm showing you that here. This part of the wave is undisturbed. The amplitude is the furthest point the wave vibrates from this undisturbed position. So this is the amplitude, and also this is the amplitude. Now the amplitude is very difficult to label on a longitudinal wave, so if this comes up in your exam, it's likely to be a transverse wave like this one. Okay, the next key feature of waves is the wavelength, so we're going to look at that now. Here's the definition. The wavelength of a wave is the distance from a point on one wave to the equivalent point on the adjacent wave. So what does that mean? Well, if we take a point on one wave, for example the top, and then measure the distance to the same point on the next wave, then that's the wavelength. And I'm showing that here. Now this works for any 2 points on the waves. So we could also measure the wavelength at the bottom of the waves like this, or even in the middle like this. Now the wavelength has a special symbol which I'm showing you here. This is the Greek letter lambda, and we'll be seeing that again in the next video. Now we can also measure the wavelength on longitudinal waves. In this case we measure from one compression to the next compression, or from one rarefaction to the next rarefaction. Okay, the next property of waves is the frequency. The frequency is the number of waves passing a point each second, and the unit of frequency is the hertz. 1 hertz equals 1 wave per second. Now in the exam you could be asked to work out the frequency of a wave from a diagram, so let's look at that now. Here's a transverse wave with the time shown on the bottom. You can see that this represents 1 second. To work out the frequency we need to count the total number of waves. We can count 1, 2, 3, 4 and 5 waves. So that means that the frequency is 5 waves per second, in other words 5 hertz. Here's another wave, and this one's got a longer wavelength. So again, to work out the frequency we need to count the total number of waves. In this case we've got 1, 2 and 3 waves in 1 second, so the frequency is 3 hertz. Now the final property of waves is called the period. The period is the time in seconds for one wave to pass a point. We calculate the period using this equation. This is given to you in your exam, but the units are not given, so you need to learn them. The period in seconds equals 1 divided by the frequency in hertz. Here's a sample question for you. A wave has a frequency of 100 hertz. Calculate the period of the wave. So pause the video and try this yourself. Okay, so the period is 1 divided by the frequency. The frequency is 100 hertz. Dividing 1 by 100 gives us a period of 0.01 seconds. Remember, you'll find plenty of questions on the
Okay, so what are the different properties of wave that we have studied till now?
We have stopped frequency and wavelength.
Good. What else you're missing? One time period.
Yeah, time periods, how to calculate time periods, 1 over f, which is 1 over the frequency in hertz.
Good. So now if we talk about types of wave, the very first one is transverse wave.
Yeah,
Transverse wave is the one where the movement of the particles or fields in electromagnetic wave are up and down. For example, if this is the motion of the wave, if this is the direction of travel, then the particles would be moving up and down. Exactly 90 degree. If this is the wave motion, the particles are going to move up and down. Got it? This is known as
right.
transverse wave, which is where one student is vibrating the rope up and down, but the energy travels along the rope towards the other student. Look at this. Now the energy is in this way, but the wave particles are always moving 90 degree up and down the wave. Longitudinal wave, for example, sound waves. The very easiest examples of longitudinal waves are the sound waves in fluids such as the air, which is generated by squashing particles together and then stretching them apart from each other repeatedly. Thus, vibrating them longitudinally, the areas of high pressure cause the particles to push apart from each other, but this makes the particles move and squash their neighbors. This high pressure is known as compression, and the area with lower pressure would be known as refraction. Now, what are longitudinal waves? Longitudinal
Longitude.
travel parallel to the wave motion. If this is the wave motion, then the particles
Okay.
are also moving parallel to it. 180. Got it?
Yeah,
Now the areas where the particles are very close together is known as compression. Where they are very far apart, less pressure, rarefaction. Then again, compression. तो ये आपके पास ट्रांसफर्स और लॉन्गिट्यूडनल वेव में फर्क होता है. So in this figure, we can also see that this is the direction of the wave travel, and this is the direction where the particles are moving, which is also parallel to the spring.
Yeah.
So how waves can be shown on a graph of displacement versus distance, and this is relatively easy with a transverse wave as well, as the graph appears like a picture of the wave, so it is easy to understand. The wavelength can be found by measuring along the graph's x-axis from one point on a wave cycle to the same point on the next wave cycle, or amplitude is measured from x-axis vertically to the maximum displacement point. Longitudinal waves are very less easy to visualize from their graphs, and making measurements from them can also be difficult. Figure C illustrates how longitudinal wave can be represented on a graph of displacement versus distance on a graph. तो ये देखें, अब ये transverse wave तो they can be directly shown on a graph, but longitudinal waves को कैसे show करना है वो आपको यहाँ से नजर आ जाएगा. Now this is the point where you will represent the rare fractions. Then this is the point where you represent compression. So compression, compression, rare fraction, compression, compression. Got it?
Yeah.
So that's how you convert longitudinal to transverse. Examples of
Okay.
transverse wave में आप लोगे तो light waves है, electromagnetic है.
Mm-hmm.
Longitudinal की examples में we have sound waves, which are caused by the oscillations of particles of medium, causing compressions and rare fractions along the line of movement of the
So
wave.
things like sound and light you can compress are longitudinals, but things that you can't compress like
Things which are not that much depending on air particles. अब light doesn't
okay,
air particles, vacuum में travel कर सकते हैं, electromagnetic
yeah.
वो भी vacuum में कर सकते हैं. They
So
don't
that they
exactly,
are
बिल्कुल वो proper
trans wave.
transverse wave है. ठीक है, they don't
Yeah.
depend on vacuum. ठीक है, if there is vacuum, there is no vacuum, they don't matter. They can travel through space as well. आपके radio waves,
Mm-hmm.
satellite communication, microwaves and infrared, they don't need air molecules. Sound waves
Yeah, so
also require
they are transverse, but
exactly.
longitudinal you need it can be compressed and uh, expanded.
बिल्कुल यहाँ पे एयर पार्टिकल्स की गेम है, because if you're going to bang a table which you are sitting on right now, you have a table in front of
Yeah,
you. If you bang a table, the other end of the table would hear the sound along the table. Solid particles में से vibration होगी, तो वो एक से travel होगी. You can't just bang
but
a
the people closer to me will hear it louder. It will
exactly
be
बिल्कुल वो
compressed
बहुत
compared to
compression
those
बनाएगी.
at the other
Exactly.
side.
बिल्कुल. So they depend on air particles. आपका जो speaker है, speaker भी vibrations है. Speaker is nothing.
Yeah,
It does not itself produce a sound. Speaker converts electrical sound to sound wave. How electrical wave है?
y-
आपका USB में
yeah,
songs है, it's an electrical wave energy. You have studied in work energy power में हमने देखा था electrical energy to sound energy convert हो रहा है. Nothing is lost. बस वो convert कर रहे हैं air particles के अंदर. Areas of
right.
higher pressure and lower pressure in the air continue the movement of vibration. An area of a higher pressure will occur when the particles are on either side displayed towards it. This means particles are displaced in opposite direction towards each other, that they squash together and they increase the pressure. अब माइक्रोफोन की भी यही एग्जांपल है, एक वाइब्रेटिंग कोन है, यहाँ से यू कैन सी देयर इज कंप्रेशन, देयर इज रेयर फ्रैक्शन, कंप्रेशन, रेयर फ्रैक्शन, कंप्रेशन. यहाँ पे साउंड जा रही है एंड इट इज बीइंग डिस्प्लेस्ड इलेक्ट्रिकली. दिस इज नोन एज अ सीआरओ, कैथोड रे ऑसिलोस्कोप एज वेल, जो कि डिस्प्ले करता है वेव का इमेज. यहाँ पे यू कैन सी दिस इज अनडिस्टर्ब्ड एयर, बट द मोमेंट इसमें साउंड आ रही है, कंप्रेशन, रेयर फ्रैक्शन,
Yeah,
कंप्रेशन, रेयर फ्रैक्शन. So here you can see these as well. Then epicenter, ये seismic waves are also longitudinal. Earthquake की जो waves हैं, क्यों? How are they longitudinal?
because you can compress them.
They are traveling through a proper medium. Vibrations है, वो भी तो vibrations ही हो रही हैं. There are
Yeah,
points of compression. There are points of rare fraction in an earthquake wave, seismic wave as well.
yeah,
फिर यहाँ पे देखिए, this is rare fraction compression, rare fraction compression. So
yeah.
transverse wave is the wave in which oscillations occur perpendicular to the direction of movement of the wave energy. Longitudinal wave is a wave in which the oscillations occur parallel to the direction of movement of the wave energy. Compression जहाँ पे particles बहुत close हैं, और refraction जहाँ particle oscillation बहुत they are further apart. And that is the end of your topic number 3A. These are the questions that you have to solve today as well. Let's watch a video, and then I think
Okay.
we can start a bit of topic 3B as well. Okay,
I
let's.
think it's just better to start new topic. I think that's better.
You think that's it for today?
No, I think better to start new topic instead of questions because
Yeah,
the
we will
more
start
the
question.
more thing we
Yep.
Because
Don't worry
question I
about
can do
time.
on my
We
own
have a
time as well.
lot of time. Okay, we have a lot of time to complete the syllabus. We have like 2 months. Okay, 1 month would be there just for past papers, and you don't have any past papers more than 7 to 8 years of your syllabus as well. Let me show you one thing, and then let's start topic number 3B. Transverse. There's just one last video. We'll see that. That's the whole summary of topic 6A, what we're going to look, and then we'll start with 3B. Okay.
Miller just allowed a message way over Jones.
The first thing to understand about waves is that they transfer energy from one place to another, but they don't transfer any matter. So when light waves pass from a phone screen to your eye, or sound waves pass from the speakers to your ear, only energy is being transferred. Sometimes, though, we can interpret that energy as meaningful information, which is why our brain is able to build up images and tunes from the light and sound that it receives. To travel from one place to another, the waves vibrate or oscillate, as we can see in this displacement distance graph. The distance is how far the wave has traveled from the starting point, while the displacement is how far from the equilibrium point the wave has oscillated, so how far it's gone up or down. The maximum displacement is known as the amplitude, while the distance of one entire oscillation is called the wavelength. So that could be from equilibrium, up, down, and back up, or it could be from the very top of a wave, which we call the crest, down and back up to the next crest. It just has to be one entire oscillation. And the opposite of the crest is called the trough. Now, sometimes you might see a displacement time graph instead, which looks pretty much the same, but because we have time on the x-axis instead of distance, the length of one complete oscillation would be the time period instead of the wavelength. And the time period is just the time it takes for one complete oscillation. The benefit of knowing the time period is that we can then use this equation here to work out frequency, which is measured in hertz and is the number of complete oscillations per second. To see how it works, imagine that each oscillation takes 0.5 seconds. Or in other words, the time period is 0.5 seconds. This means that there must be a total of 2 oscillations per second. So the frequency is 2, which is what we'd get if we did 1 divided by the time period of 0.5. We can also use the equation the other way around. So time period equals 1 over frequency. So if we were told that the frequency of a wave was 4 Hz, which means 4 oscillations per second, then to find the time period, we'd just do 1 divided by 4, which tells us that each oscillation must be 0.25 seconds. The next equation to know is that we can find the speed of the wave, so the wave speed, by multiplying the wavelength by the frequency. So basically we multiply how long each wavelength is by how many there are per second, and that will give us the total distance they travel per second. To see how this works, let's imagine we had a sound wave that had a frequency of 400 Hz and a wavelength of 70 centimeters. What is its wave speed? Well, in this case, all we'd have to do is convert the 70 centimeters to 0.7 meters, because we always want our wavelength in meters, and then multiply it by the frequency of 400 Hz, which gives us 280 meters per second as our wave speed. The last thing we need to look at are the differences between transverse and longitudinal waves. In transverse waves, the oscillations are perpendicular to the direction of energy transfer, or the direction in which the wave is moving. Which is why on our drawing, the vibrations are going up and down, whilst the overall wave is travelling from left to right. Most waves we can think of are transverse, including all electromagnetic waves, like light and radio waves, ripples and waves in water, and the waves of strings like on a guitar. Longitudinal waves, on the other hand, have oscillations that are parallel to the direction of energy transfer. This one's a bit trickier to get your head around, but basically it leads to some regions that are more spread out, and other regions that are more compressed, because the wave's vibrating back and forth. In motion, it would look as if this area of compression is moving from the left to the right within the wave. Examples of longitudinal waves include sound waves and some types of shock waves, like seismic P waves. Anyway, that's